So, in the last lecture we discussed sort of a background into wavelets, right. What are wavelets, why do we need wavelets, what are the shortcomings of the discrete Fourier transform and so on, right. And we said that one of the important things that motivates wavelets is multi-resolution. That means we want to expand a function at different scales, at different resolutions, right, and that has applications from denoising to efficient signal representation, etc., etc., right. So, now we will get into the details of the of wavelet analysis. The first and foremost to get towards this is understanding what multi-resolution property is all about. Okay. So, let us start with the definition first. Let V suffix j for j equals dot 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 minus 2 minus 1 0 1 2 dot 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 be a sequence of subspaces of functions in L to R, right. They are basically square integrable functions. The collection of spaces which is all Vj, j belongs to the set of integers, is called a multi-resolution analysis with a scaling function phi with the following properties. So, let Vj j equals dot 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 minus 2 minus 1 0 1 2 3 so on be a sequence of subspaces of functions in L to R, that is all square integrable functions, and the collection of spaces Vj, j belongs to the set of integers, is called a multi-resolution analysis with a scaling function phi if the following properties hold good. Okay. Let us see what the properties are. The first property is the nesting property. What it means is the space Vj is contained in Vj plus 1, that is V0 is contained in V1, is contained in V2, so on. So, this is a containment property, this is called nesting, and we will see very carefully through illustrations and examples what this containment property is pretty soon. Okay. So, I think you can get an idea that one subspace is contained in the other subspace. So, this picture should be there in your mind. The second is closure. the closure of the union of all these spaces is essentially, I will put 2 here, the original space of all square integrable functions, that is the closure of the set of spaces covers L2R, which means that every function in L2 has a representation using elements in one of the nested subspaces, right, which also means every function in L2 has a representation using elements in one of the nested subspaces. I would say this is sort of the meaning or interpretation of this property. Okay. I think it will be useful to picture how these spaces are, right. This is our V0 space, then this is our V1 space, then this is our V2 space, and so on. I mean, you can kind of imagine that the signals are confined in those spaces. I mean, what is in V0 is contained in V1, what is in V0 and V1 is contained in V2, and so on. So, this idea has to be clear. The next property is shrinking. That means, if you look at the intersection of all these spaces, this should be trivially the 0 element. You could call it a vector, or you could call it a function, or whatever, 0 function or 0 element, okay. And you could guess this, it should be true because it is a linear vector space. Then is the scaling property. This is important. If f of t belongs to the space Vj, then f of 2 power minus j times t belongs to V0. I used deliberately the radix 2 here. You could use essentially any a, right. You could use any a power minus j belongs to t. I mean, I just used this because we will deal with Haar wavelets in particular, and we see a dyadic representation there. So, this 2 was used, right. Otherwise, you do not have to have 2, you could have a 3 if it is a triadic decomposition, you could use 5 if it is a phiadic decomposition, or in general for any p-adic you can have a p power minus j, okay. So, this is just a small note. Then there is something called shift orthonormality. What it means is as follows. the function phi belonging to V naught, and when I say phi, it is phi of t here, and the set phi of t minus k, all its time translates, k belongs to the set of integers, is an orthonormal basis for the space V0. What it means is, if you take the inner product of the function phi of t with phi of t minus n for some integer n, this must be 0. Of course, the normality would ensure that if you take the integral norm for these functions, it has to be 1. I mean, if you take the integral of phi square t dt or phi square of t minus n dt, that has to be 1. Of course, when you look at this equation, inner product of phi of t with phi of t minus n, this is equal to 0. This would imply obviously for n not equal to 0, because when n equals 0, it is coinciding, right. I mean, this is never 0. So if all these properties are satisfied, then it forms a multi-resolution analysis. So let us just recall, one is the nesting property, that is, you have a sequence of subspaces that are nested, okay. Then there is closure, that means every function in L2 has a representation using elements in one of the nested subspaces, right. This is akin to saying that you know, I mean for example, if you think about any square integrable function and I have a Fourier basis for that, right. I mean I can think about having a Fourier basis for that, provided it satisfies certain conditions. Now similarly here it is saying that every function in L2 has a representation using elements in one of the nested subspaces, but the distinction with this is certain other properties like nesting, shrinkage, scaling, shift orthonormality, etc., which is not there in perhaps certain other transforms. Nesting is one of them. Then shrinking. So this is a very trivial thing. If you take the intersection of all these subspaces, it should be trivially the 0 function, okay. Then scaling. If f of t belongs to Vj, then you take a scale of that which with 2 power minus j. So f of 2 power minus j t belongs to V0, and shift orthonormality, the function phi of t and all its integral translates, they form an orthonormal basis for this space. Now it will become very clear if we see through some examples. Let us see this. Through some examples. So we start with a definition. So we will start with the simplest wavelet, which is the Haar wavelet, and then we will progressively advance, okay. The Haar scaling function is defined as follows. Now phi of t is 1 between 0 and t less than 1, and it is 0 0 else. So, if you just plot this, this is how it would look. It is like our simple step pulse that we are used to, right. Now, this function has finite, or I would say compact support, and you can realize translates of this function by time translating phi of t through integral time steps, right. And this is very important. This compact support is very important because unlike the sine cosine bases that form essentially the basis for the Fourier expansion, the bases here have compact support. You look at sine cosine, it basically extends from minus infinity to plus infinity, and this is one of the fundamental questions that we asked in the very beginning for signal representation. Do we need functions which are not finitely supported to expand a function which is finitely supported? It is a commonsensical question to ask. I mean, I have a pulse maybe from 0 to say 5 seconds, some t seconds, some arbitrary pulse, and why would I need sines and cosines in an infinite dimensional basis, I mean whose dimension is basically infinite, to expand this signal, and each of the basis functions themselves are not compactly supported. Can I represent functions using a compactly supported basis set? Okay. So, if you ask this question, this is where we are sort of alluding ourselves to. Okay. Just another detail, phi of t minus k is phi of t translated by k units to the right if k is a positive integer. I mean, you can translate it to the right or to the left. Now, once we get this picture of compact support and translations, now we are ready to define this space V0. V0 is a space of all functions of the form sigma ak phi of t minus k, where k belongs to the set of integers and ak's they are basically real numbers. Now, how can we picture this function? I think one of the ways we can picture these is as follows. I have time step minus 1, 0, time step 1, time step 2, time step 3, time step 4, 5, so on. Now, there is say a minus 1, this is say a 0, this is A1, this is say A2, this is say A3, right. You observe these discontinuity points. Right, so on and so forth. So this is like our A minus 1, this is A naught, this is A1, this is A2, this is A3, dot dot dot. Now, of course, you can clearly observe the shift orthonormality, right. I mean, if you take phi of t with phi of t minus 1 for this simple scaling function, it is basically 0 because the support, I mean, the overlap is essentially 0 between phi of t and phi of t minus 1, right. So, you now can appreciate the idea why you want to have time translates starting from a simple box car function. Now, let us go a little further. So, we shall start with a structure at half the time duration. That is, we start with phi of 2t. So, let us sketch how this looks. Now, phi of 2t is 1 between 0 and half, and it is 0 otherwise. Right, you plug in when t equals half, it is 1, t, you plug this into the function. So, you can really see this what is happening. So, therefore, if I have numbers that are greater than a fraction, greater than 1 here as the coefficient of t, I am basically shrinking in time, and if it is phi of t by 2, t by 4, t upon 8 and so on, I am basically stretching the function. So, I can stretch or I can compress depending upon how I modulate the coefficient in front of t, right. And again I can think about time translates of these. Now, let us see this a little bit further. Now, consider phi of 2t minus k. Now, this can be written as phi of 2 times t minus k upon 2, right. So, what does this mean? Now, I have a phi of t which is basically I mean if I take this function, this is basically phi of 2t which is k translated, right. Or if you write it in this form, you start with the original function phi of t and basically you shrink it by a factor of 2. If you basically take a translation k by 2, k upon 2 steps to the right and followed by a shrinking, this is what you are going to get. So you should be able to interpret both of these starting from this function phi of t with translation and shrinking, or directly sketching of phi of 2t and then basically looking at a time translation, right. So if you sketch this, how does it look? Let us suppose we choose k equals 1 . This is how we will have, okay. Observe the discontinuity point here. This is 1, indication this is 1. This is essentially translation of phi of 2t to the right. For the k equals 1 case. Now we get this picture, right. So you have a space V0, you have a space V1, so on and so forth. Now V0 is basically all V0 is a space of all functions which can be realized using the basis phi of t minus k, right. So and now V1 would be basically using the basis phi of 2t minus k, right. That picture should become pretty clear for us. Now geometrically V1 is the space of all functions of the form summation k belonging to set of integers ak phi of 2t minus k, where ak is some real number. Now you may wonder where the discontinuities are, and the discontinuities exist at half integer multiples, right. The possible discontinuities exist at half integer multiples, that is 0 plus minus half plus minus 1 dot dot dot. So let us carefully analyze and see what this nesting property is, okay. Now phi of 2t belongs to V1, but does not belong to V0, right. What is V0? V0 contains some signal which can be expanded using phi of t minus k, where k is some integer, set of all integers, right, negative and positive integers. But this function phi of 2t, which is basically a boxcar function which is 1 from 0 to half and 0 else, cannot be realized using V0. Okay. So phi of 2t belongs to V1 but does not belong to V0, since phi of 2t is discontinuous at t equals half. I mean, if you think about it in the form of sets for these discontinuities, I think it is much easier to picture this way. Discontinuities in V0, they exist at 0 plus minus 1 plus minus 2 dot dot dot. But if you think about the discontinuities in the space V1, that is at 0 plus minus half plus minus 1 plus minus 3 upon 2 and so on and so forth, which means any function in V0 is also contained in V1. But not the other way. This is an important sort of observation that you might want to think about, right. So we can conveniently say that V0 is contained in V1 but not the other way around, which is what we wrote in the very beginning as one of the properties, that it was the first property on nesting of these subspaces. V0 is contained in V1. This is what it is. Now if we go forward, Vj has all the information up to a resolution 2 power minus j, right, and as you increase j, your resolution is becoming finer. That is, as j increases, the resolution is finer. And it is straightforward and quite intuitive. Imagine, for you to imagine functions of the form f of some a power j times t, where a is a real number. Now, where is this useful? Suppose I have a short burst of some time, let us say root 2 seconds or 1 upon root 2 or some very small time, right. I can figure out to which space it belongs to, and I can go to that level of detail that I would want to in the appropriate space, right, rather than having the same bandwidth across all the filters, or if you think about in the language here in terms of saying that we give the same resolution for all the functions, we say we give a sort of a different resolution for different scales. That is the whole idea, and you have to get that picture very clear in your mind. All phi of t minus k's, all phi of 2t minus k's, all phi of 4t minus k's, all phi of 8t minus k's, so on and so forth, right. If you imagine this space, you can think about, yeah, I can go to whatever resolution that I want in whichever space, and I can expand a function in that space, okay. And I have this nesting property, one subspace is contained in the other. Now, let us go a little further. We need a procedure to do signal decomposition. So, let us see the intuition here before we proceed formally. I mean, if you think about the history of mathematics, at any point of time, first you have to have some intuition, some idea to start with. That is a key thing, and then you start building the theory rigorously, formally, right. Nobody starts with some, I mean, you have some definitions. If you know those definitions, it is great, but if you do not, you start with an idea from scratch, and then post that you start building things, okay. So, let us see this intuition here. So, let us start with the space V0. If you look at the integral norm, square of the integral norm of phi of t minus k, well, this can be written as integral minus infinity to plus infinity phi square of t minus k dt, which is basically phi of t minus k exists from k to k plus 1, and this is 1 square is 1 dt, and this is basically 1. And if you take the inner product of phi of t minus j with phi of t minus k, this is basically given by this integral, which is 0 for j not equal to k. If j equals k, of course it is 1. So, how do you visualize this? So, you have some j plus 1 dot 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 some k plus 1, and you have this, this. Okay. Now, we have established normality, we have established orthogonality, it forms an orthonormal basis. We have understood how these functions look with scaling. It could be a stretch or it could be a shrinkage. Now, we are ready to basically state a result which is formal, and we state this as a theorem. The set of functions 2 power minus j upon 2 phi of 2 power j times t minus k for k belonging to a set of integers form an orthonormal basis for Vj, space Vj. Proof is pretty straightforward. I will just give you a sketch. Now, you start with the norm of 2 power j upon 2 phi of 2 power j t minus k, the integral norm. So, basically this is integral minus infinity to plus infinity. You have 2 power j, this j upon 2 with j upon 2 will be 2 power j, then this is phi square of 2 power j times t minus k dt, right, and this is basically 2 power j. You pull out, and the limits, this is existing, basically you pull 2 power j out, you get t minus 2 power minus j into k, right. So, therefore, this exists from 2 power minus j times k to 2 power j times minus j times k plus 1, right. So, there is 2 power minus j you pull out, k to k plus 1, and this is 1 square dt, and this is basically 2 power j times, this is 2 power minus j, which is basically 1, and then you can quickly check for orthogonality, that is choose some k1, choose some k2, and like what we did earlier, right, where we had phi of t minus j and phi of t minus k, for k not equal to j you could just do the same thing, except that now you have two shrinking functions or expanded stretched functions, and they do not overlap in their support, right. very important for different time translates. It's very important. There's a small typo here that I just saw right now. This negative, there should not be a minus sign here. It is 2 power j upon 2, I mean, because it has to integrate to 1. So what it means, if you put in the formal language, the inner product of 2 power j upon 2 phi of 2 power j t minus I, take the inner product with 2 power j upon 2 phi of 2 power j times t minus some k equals 0, because I is not equal to k and they have disjoint supports, and that sort of proves this result. We will stop here.